Hey everybody, this is the last problem. So this one is slightly different. It's a little bit more complicated. I got to look at things kind of backwards, forwards, and side to side. So we have a chest of toys. Got to be moved out of the way. So this kid Tommy ties a string. Blah blah blah. That's all unimportant information. So what the important information is the tension force, 40 newtons, the acceleration, and the 100 Newton chest. So that 100 Newton chest tells me that that is our weight, Fg, of 100 newtons. Alright, but we also have, it doesn't specifically say, so I just like to bring it up and to the right, 40 newtons at 35 degrees. AH is above horizontal. Alright, so whenever you see the arrow and the angle, you break them apart. This is a tension force. So in this case, your Fty, when it's with respect to the horizontal, is your tension, Ft times sine of the angle. And your Ftx is Ft, sorry, a little messy there, times cosine of the angle. Where this one is our Ftx, the side of the triangle, and our vertical side is the Fty. So our Fty is our tension force, that's 40 times the sine of 35 and 40 cosine 35. 40 sine 35 is 22.94. 0.94. Pen's being a little funny today. 22.94 newtons. And 40 cosine 35, 32.77 newtons. Alright, so we broke this into pieces. There is friction. We know there was friction involved. We just don't know what it is yet. But we will get to that. So we have the following. Redrawing our free body diagram. Force of gravity still pulling down. We have an upwards force from Fty of the 22.94 newtons. 22.94. Sorry, my pen's just being a little funny today. That's Fty equals 22.94 newtons. We have our Ftx of 32.77 newtons. And we also, since this is still on the floor, we know we have to have a normal force. And the normal force, because this is on the floor, it's on something, has to be equal to whatever is left over that the tension vertically is not pulling up. So our normal force has to be our 100 newtons minus our 22.94 newtons, because it has to take up the rest. The floor doesn't have to push up with the full 100, but it has to push up with something. That something is 77.06. So our normal force is 77.06 newtons. And when we're figuring out friction, having that different number for the normal force, we can't use the 100, having that different number is going to make a big difference. Alright, and there's one force I haven't yet drawn, and just because it's the way I drew this, I'm going to draw it over there. That is our friction force. Okay. So, we have to look at certain information. First of all, that is my weight, that's my Fg. I need to find my mass. So mass is Fg divided by 9.8, 100 over 9.8, 10.20 kilograms. So 10.2 kilograms is our mass, and we know our acceleration. So if we know our mass and our acceleration, we know our net force. Fnet is mass times acceleration, and this is sort of the backwards part I was saying at the beginning of this video. If anybody heard that, that was my cat. Yep, there she goes again. 1.2. So 10.2 times 1.2 gives 12.24. So our net force is 12.24 newtons. Well, our net force, since all the verticals cancel because we're on top of something, has to be our net force horizontally. So our net force horizontally is all of our right forces, which in this case is just Ftx, minus all of our left forces, which in this case is just Ff. But we know it's being moved out of the way. Keyword is moved, which means it is sliding, or it even says, since it has an acceleration, that means it's sliding. So the force of friction has to not only be not equal to 32.77, it has to be, my cat's really going at it, has to be the kinetic friction force. So we kind of set up this new little equation that we can solve to figure out what our kinetic friction force is. And that I'll do right down here. 12.24. All of these equations are related is the point I'm trying to get across with this problem. 12.24, our tension force is 32.77 newtons. Positive number means our net force has to be to the right. So we've got to subtract whatever the force of friction is and solve for that. You get 12.24. You get a force of friction, that is kinetic friction, of 20.53, and it's going to be a negative number, or you can just say 20.53 newtons to the left, as drawn, because we drew it to the left. So that's our kinetic friction force. So we got that part done. But we also have to find the coefficient of friction. And just like the last problem, our coefficient of kinetic friction is our kinetic friction force divided by our normal force. And this is where this different number comes in to play. Because we're taking some of the stress off of the floor, we're not interlocking those pieces anymore. We're helping to pull those pieces apart. The friction is already somewhat broken. We don't have to go as high on those hills. So our number would go lower. If our if our normal force were higher, our friction force would be higher. But because we've taken a little bit of friction of the normal force away by pulling upwards and helping with it, our friction force has gone down. So our coefficient of friction is 20.53. This is all unitless, so we don't have to worry about units because newtons will cancel with the 77.06 newtons of the normal force, and you get a coefficient of friction. I'm probably on top of my video, on top of myself. If I am, I apologize. Over 77.06. Let me rewrite that up here just in case. Mu k is 20.53 newtons over 77.06 newtons. Newtons cancel, and you're left with a mu k equal to 0.266. Keep 3 decimals, you can do 0.27 as well. That's totally fine. We know it's a mu k again because it's accelerating. Accelerating means it has to be moving. If it has to be moving, then it's kinetic. All right, so like I said, this is kind of a weird problem. It's a backwards problem. It's one we haven't quite done in the past, but something we're totally capable of doing. It's just combining things sort of in the backwards way. We first took our force, our angled force, broke it apart, used information that we knew, such as how to find the normal force, and using that with information involved in the problem already, the acceleration and side-handedly the mass, to figure out what the net force is, using the net force from Newton's second law, which is right here, and the net force as just all the left forces, all the right forces minus all the left forces, set up a separate equation which allowed us to find the kinetic friction force. Finding that kinetic friction force along with the previously found normal force allows us to find our ultimate answer of our kinetic friction coefficient. So hopefully this helps. Hopefully you will do well on the rest of this worksheet and the similar problem that you see. So good job, and again, I will see you all on Friday because I see everybody then. All right, perfect.